Okay, thank you. So I'm Eric. This is joint work with Pierre Dagan at UPMC in Paris and Nicolas Tabarot in RIA in Nantes. So I'm going to talk about partial type equivalences for dependent interoperability. What's that? Well, we've heard some of it. Okay, so as you know, your dependent types like size index vectors are great. But for some programmers, they might be a bit demanding to work with at times. But they, on the other hand, they give us a number of nice properties for our programs and robustness guarantees, right? On the other hand, working with lists, simple lists is a bit more relaxed, but doesn't give us as many guarantees about the behavior of the programs. So dependent interoperability is actually concerned with the sound interaction between both type disciplines. So this is, in a way, similar to gradual typing in that it will require some kind of dynamic checks to travel between both worlds. But it's a bit more than that because there's the data constructors are different on the two sides. So you actually need to marshal your structures. OK, so why would you want to do that? There are different use cases for that. So you may have, let's say, a simply typed library that works on lists that you want to reuse in a dependently typed context. Or vice versa, use a dependently typed library in a simply typed context. I'll show you that you can even combine both to actually embed dynamic verification in simply typed components through types. And you can use that to make extraction of dependently typed programs safer. OK, so the first case, for instance, you may have your typical function that claims to reverse list with a list-to-list type. And you have at hand an indexed vector, then you may want to say, OK, to be able to use this reverse function, I need to lift it to this for all vacant to vacant type. And as you see, there's some stronger guarantee in this type that the output is of the same size as the input. And this, therefore, would have to be checked at runtime because the first function may actually be wrong in that respect. Vice versa, you may have your safe tail function that takes a vector of size n plus 1 and gives you back a vector of size n. And you want to use it with a list, simple lists. Then now we have the constraint on the fact that tail cannot be called with empty lists. And this disappears now in the type system. So we'll have to check at runtime that the argument is actually not empty. OK, we can combine both lifting operations by starting with a list-to-list function, lift it to a dependent type signature, and lift it back to a list-to-list function. And by doing that, what we've basically done is to embed checking of dependent contracts, as in Racket, basically, but by going through a type signature. OK, so that was the third case. And the fourth case is extraction of dependently typed programs. So as you might know in Coq, well, usually you use some type dependencies when you do your development. And at the time when you extract to OCaml, well, many of that goes to the trash bin, which also sacrifices potentially type safety if you are in an open world. As an example of this, this is a stack machine example from the Adam Schlipalas book, where we have an execution function that runs instructions on stacks. Stacks are indexed by their size. Instructions have two indices, one for the size of the stack before running the instruction, and the second one that says what's the size of the stack after running the instruction. This type information through indices allows you to have this nice direct disconstruction, which basically means that your program grabs two elements from the stack without actually checking that there are two elements on the stack. And this is fine for Coq because the type discipline ensures that. However, when you extract this function to OCaml, you will see in the output code that there are some magical conversions there. And those are like injection into magic. And the dangerous one is the projection from magic, which assumes that you have elements on the stack. And if you actually run this function from the command line, you can get into a segmentation fault. OK? So if we have a dependent interoperability framework, we can take our exec function with its dependently typed signature lift it to a simply typed signature that manipulates basic instructions as an inductive data type and plain lists as stacks. Extract, so we do this lifting in Coq, then we extract to ML, and then if we execute our simple instruction for addition on an empty list, then we get a runtime exception instead of a segmentation fault. Okay, so what this work is about is basically partial type equivalences as a constructive foundation for dependent interoperability. Concretely, this means we have a Coq framework, the ICOC, that captures a notion of partial type equivalences such that the user of the framework has to provide some first-order equivalences, like the fact that somehow lists and vectors are related. I'll make that precise in a minute. That's what we call a dependent equivalence. And once the user does this, the framework provides higher order equivalences, which are verified by construction, between functions that operate over those types, right? So you get basically an equivalence between functions on list and functions on vectors. That's what we call a partial equivalence. And this equivalence is actually constructive in that the proof of the equivalence is actually the algorithm that does the conversion. And so therefore, this is the lifting operator that you want, and it's by definition correct. Okay, so let's talk a bit about equivalences. So Jasper already told you about the total normal case of equivalences between types, which is when you have basically an isomorphism between both. You can, with the usual equations, that if you go back and forth, you go back to the same place. And notice that in this case, we rely on equality in both types for these equations, and we assume that the functions are total, right? So that's your basic notion of type equivalence. Can we use this notion of type equivalence to relate lists and vectors? Well, I guess I wouldn't be here if you could. So it's easy to see that you can go from a vector to a list. However, in the other direction, given an arbitrary list, going to some vec n might not always be possible. For instance, if you have a list with 3 elements and you want to get a vector of type vec2, then obviously that's wrong. Therefore, this is not really an equivalence. However, it's also not different beasts, so there has to be some notion of partial type equivalence to relate both types. And basically, we characterize that by relaxing a bit the framework and allow basically the morphisms to be partial and therefore admit cast failure in a way, so that you can see that as functions over the option monad. And here the equations are a bit relaxed in the sense that first they use the monadic composition, and second they don't require equality. They use this partial order, which is the extension of equality up to failure. Okay. Once you have this, so the other equation is the same. We can generalize this one step further to arbitrary monotone functions on any preorder, basically. And so that's like Huntington Galois connections. We actually use that for higher order equivalences. So I told you that we are going to talk about the equivalence between a function over a list and a function over vectors. And so let's look at that in a bit more details. If we start with our list-to-list function, we lift it to this dependently typed signature. We lift it back to list-to-list. As I've told you before, this basically bakes in some runtime checks in the function. And here the equation tells us that the double lifted function can fail more often than the original function. Okay, so the blue arrows are total, but it's the arrows in the domain that are partial. All right, so this is like the general notion, and this has nothing to do per se yet with dependent interoperability. The idea is how can we use this notion of partial type equivalences for the specific case of dependent interoperability. So in that case, we are interested in relating index types to simple types, and the idea is that we do that through subset types. Okay, so index type here is like our vec n. And here list, and we go through a subset type that basically separates the computational content from the logical invariant of the structure, right? The logical property. Okay, the meaning of the index, right? Because when you say vec n, well, n could be actually representing different things, not necessarily the length of the list. Okay, so the equivalence between an index type and the subset type that captures the meaning can actually be total, but the one between lists and lists such that the length is of size n is a partial equivalence. Therefore, by composition, we have a partial equivalence between vec n and list. Here, if you look at this triangle, you'll see that the n is kind of floating around. So what we want to establish is actually a dependent equivalence, what we call a dependent equivalence between vec and list. And for that, we have to show that for all indices n, there exists this diagram. Okay? Once we have those things, we are interested in using that automatically to have automatic liftings between types. Obviously, if we want to go from vectors to list, it's fairly easy. We use the total equivalence to go to the subset type, and then we drop the refinement. On the other hand, in the other direction, we start with a list, and now we need to figure out if we can go into the subset. This depends on whether n is actually free in the context at that point. If it is, then we need to have a synthesis, index synthesis function that basically tells us what the canonical n for this simply type structure is. And if it's bound, then we need to check that we are allowed to actually go in that direction. If we manage to inhabit the subset type, we can use the other side of the equivalence and go to vectors. Okay, so that's basically the core of the idea. So in practice, with our framework, someone wants to start by establishing a dependent equivalence between lists and vectors, needs to first give us conversion functions between indexed and subset, give us a checkable index predicate, like is the length equal to n, and an index synthesis function. Given a list, what's the n that corresponds? And simple proof that this makes sense. When I say simple, I mean software foundation levels, right? So proofs I can write. The others I can't. Okay, so the ones you get for free is higher order equivalences. So what is that? It's basically, so all this in Coq is type classes and instances that allow deriving new instances of type classes and so on. And so we have one particular case that says that if you have two dependent equivalences, B1C1 and B2C2, then we can actually infer dependent equivalence between a function over B1, B2 and a function from C1 to C2. Okay, and so that's quite technical to prove. So that's where the homotopy type theory expert is helpful. You can find more details about this in the paper. And as a result, we have an extensible library of type classes and instances that allow you to derive those equivalences. Okay, and again, the framework is constructive in that the proof of this equivalence is the lifting operator. Okay, so let's go back to our examples. We have the tail function with its dependently typed signature, and we may want to lift it to a simple pop function over list. So this is what the programmer has to write in Coq to do that. Basically, they define that pop, specify the target type of pop, and call this lift operator that we provide. What this does is that it first takes the source type and brings it into the monadic setting, and then looks for an instance that would allow it to establish the equivalence. In that case, it finds the equivalence between vectors and lists, and this is exactly the dependent equivalence that we're interested in, so it works out of the box. That's somehow the simple case. A more interesting case is the execution of instructions over index stacks that I mentioned. So we have exec, and I said if you want, before extracting to a camel, you might want to lift it first to a simple execution function with plain simple instructions and lists as stacks. So the first thing that we'll do is go to the monadic setting, and then we need to realize that given a simply typed instruction, we need to somehow find the dependently typed instruction that corresponds, and this implies finding both indices n and m. However, this n is a bit more problematic because it models the input the size of the input stack, and given a simply typed instruction, you can just make out the n that fits, right? Therefore, the equivalence that you can establish between instructions, dependent instructions and simple instructions is actually a pointwise equivalence given a fixed input stack. Okay? In the exact function, the n actually comes from the second argument, right? So that's where the type class machinery is helpful, because this, when it tries to unify here, it fails, and it therefore tries a permutation of the argument. So it's now trying to, he swapped the two first arguments both on the top and below, and the system tries to find now an equivalence that justifies equivalence between those two types. And this is a rather nice case, because if you look at the last row types, well, and we consider this pointwise equivalence among instruction and the equivalence between stacks and lists. This is exactly what corresponds to that part. And we can then compose this equivalence with the fact that our pointwise equivalence holds for all n, and the equivalence that we already have over stack and list to actually put the two function types related. Okay, so this is all fairly complicated, but that's not exposed to the user. The user actually just writes this, which is simple exec. It has this type, and I'm using lift2. So lift2 is another lifting operator we provide to get rid of two indices, and that tries this swapping. And if you look at the extracted code, it's basically the monadic code you would write to do the conversion if you would do it yourself, except that it's done automatically by the type class resolution mechanism, right? So type classes both do the proof and generate the algorithm for you. Okay, one last word about how we deal with cast errors. So you might have noticed we are in the monadic setting in Coq, which means that when we go to a camel, if we don't do anything special, our functions on list is actually going to give a monadic signature as well. We can actually define a specific error monad in Coq that erases itself and projects the failure case to the runtime exception in using the fact that ML has runtime exceptions, and therefore the output signature is actually what you would expect programming from ML in a direct style. Okay, that's it. So we have presented this notion of partial type equivalences for verified dependent interoperability that provides constructive foundations and a verified implementation of dependent interoperability over Coq, both inside Coq and through extraction. The code is on GitHub if you're interested, and I'll be happy to take your questions. Thank you.
Thank you.
David Christiansen from Indiana University. If you were wanting to support extraction to something other than ML using this technique that did not have as rich of a type system as ML, say you wanted to extract to JavaScript or Scheme or something, is there a way that you can extract to a language which only has one type using this, and do the same techniques scale up to that sort of a situation?
Yeah, it would basically. So the only thing you need to do is to be able to go up to the type that your target language supports, or type signature that your target language supports, and then this is supported by this partial equivalence. So basically, you would get back the gradual typing stuff of, oh, is it an int? Yes, it's an int.
Phil Wadler, University of Edinburgh. Two different questions. One is DI Coq just a library on top of Coq, or did you have to change Coq itself?
It's entirely a library. No change, just type classes.
Good. And the other question is, so if you wanted, this is related to the question about doing something like Scheme, I think. Let's say I want to embed Scheme in Coq, and so I want to introduce a universal type, and then have automatic embeddings into it. Does that fit in your framework? Have you tried doing that?
So I
haven't write it down so I could study it and steal it.
So you're welcome to try it before I have time to try it. I hadn't, so I haven't tried it. I'm fairly confident it works for knowing how this this works already. But I think it's a good, double good suggestion, so it's definitely something we'll look at, if you don't.
John Hughes, Chalmers and Cubic. So if you take the tail function on vectors and then you lift it to operate on lists, in the implementation after extraction, does that mean that you copy the list twice in order to take its tail? Or is that optimized away?
Okay, so no, so there's no optimization at all yet, right? This is like the semantic framework, and basically each time you cross the boundary, you use these conversion functions that reconstruct, okay? And the boundaries are done, the conversions are done at the boundaries, right? So if you have a function that's inside is recursive, you will stay with vectors. But when you go back to the list world, you'll get a new list, and then if you do recursive interactions at the boundary, then you'll get these pathetic cases that you also have basically in gradual typing with wrappers going around and stuff like that. So there's been work like in the multi-language semantics to kind of recognize when you're going back and forth and try not to repeat things. That's future work, basically. We haven't had time to look yet at all those optimizations.
Hi, Neil Krishnaswamy, University of Cambridge. So I was wondering, so there are some effects.
Sorry, where are you?
Hi.
Oh, okay.
Neil Krishnaswamy,
Yes.
University of Cambridge. So there are some effects it's hard to test for, like non-termination. Do you have any way of like getting a non-terminating language to interact with Coq?
Not as far as I know. That's probably a higher. Well, I guess with monotone types, you could do something like that, right? So gradual monotone types.
Peter Michael Lasser from Grinnell College. Hey. So people brought up sort of weaker type systems, funny non-termination stuff. Have you thought about type systems that are just different, like substructural logics and things like that?
Not in this setting, where that's something I'm looking at in the standard gradual typing stuff, not as a dependent interoperability story. So could be connected as well, yeah.
Okay, let's thank the speaker again.
Thank you.
And